Hello everyone, I'm honored to share my solution for this Kaggle competition. And the entire presentation is divided into 5 parts. In the first section, I will provide a brief overview of the entire solution. In the remaining 4 sections, I will delve into detailed explanation of the 4 main tricks used in the solution. First, I will outline the inference process and the training procedure of the solution. My solution does not differ significantly from most of the solutions found in public notebooks. During the inference stage, initial speech recognition results are obtained from the audio input via Web2 Vector 2. Then in post processing stage, I use a 6-gram language model and diary and normalization to correct the prediction results of the Web2 Vector 2. And this is the training stage. I use the CDC
loss. Hello, so sorry, Hans. Are you showing some specific slides? We're only looking at the first cover page only. And yeah, or maybe you can make it bigger too, if it's okay. Sorry about that.
Oh, is this normal now?
Okay.
I think I'll go.
Yeah, that's better. Thank you.
During the training stage, I use CDC loss and to train Web2 Vector 2. And I implement 3 tricks, which is the compound data augmentation and the competition data filter and the modified linear format cosine learning rate scheduler. And I will explain these tricks in the subsequent sections. As we can see, these 3 compound data augmentation is used to train the Web2 Vector 2. Due to the significant distribution difference between the training and the test set in the competition, I think it's necessary to use strong data augmentation. And consequently, on the top of basic data augmentation, I tried 3 additional compounds data augmentations to further enhance the complexity of the training data. So this allows the model to better generalize to the test set data. First, I need to define a basic data augmentation, and this basic data augmentation doesn't differ significantly from the ones used in most speech recognition tasks. And it's a code of the basic augmentation. And this is the first compound data augmentation. I call this compound the first data augmentation as audio augmentation on a concat. Each time n samples are simultaneously taken from the dataset, then each sample undergoes transformations use basic data augmentation. The transformed samples are then concatenated together to serve as the final input for the model. The second compound data augmentation is audio segmentation and augmentation. Each time a speech sample is sampled from the dataset, is split into 3 parts of equal duration. Then each subsample undergoes basic data augmentation, after which the three transformed subsamples are concatenated together, as we can see in the figure. The third compound data augmentation is a combination of the two augmentations mentioned above, and is the most complex one. For detailed instructions, and we can refer to this diagram provided. I won't go into further detail here. During the competition, some participants mentioned in the discussion that there were noisy data within the competition datasets. Therefore, I implemented a data filter on the competition datasets prior to training the final model. The data filtering process consists of 4 steps. First, a baseline model is trained using all of the composition dataset, including both the training and validation sets. After the baseline model is trained, it is used to infer the entire dataset and calculate the normalized CTC loss for each original sample. Then, based on the normalized CTC loss of each sample, sort the entire dataset in ascending order and retain the top 70% of the data. And the code on the right is how we calculate the normalized CTC loss. And the next part is how we train the model. The entire training phase consists of 3 stages. The pre-trained model for the first stage is the Facebook Web2Vector XLSR1B, and the pre-trained model for the second stage uses the weights from the training outcome of the first stage. The pre-trained model for the third stage uses the weights from the training outcome of the second stage, and the hyperparameters for the training in each stage are the same, with the only difference being the random seed, and the hyperparameters are listed here. And it's worth to mention that I use tokenizer, same as this model. And it's worth noting that during the training procedures, I use a modified linear warm-up cosine learning rate scheduler. In the first 1,000 iteration, the learning rate linear increase from warm-up learning rates to initial learning rates. Yes, warm-up learning rates is this, and the initial learning rates is this. Then in the initial quarter of the training iterations, the learning rate decays from initial learning rate to minimum learning rate, following a cosine function. And from the quarter through half of the training phase, the learning rate remains constant at minimum learning rate. And for the remaining half of the training stage, the learning rate decays from minimum learning rate to 0. Again, following a cosine function. The reason I use this learning rate scheduler is that when employing the regular linear warm-up cosine strategy, the model's performance on the validation set always reaches its peak in the final few iterations. Therefore, I aim to extend the training phase with a small learning rate as much as possible. There could be another implement method that the outcome achieved through this approach is acceptable to me. And lastly, I trained the 6-gram language model. The corpora I used are IndiCrop V1 and IndiCrop V2. To pre-process the corpora, I need to remove any characters in each sentence that are not part of the Bengali language, including punctuation marks. Then each sentence is normalized. Then I merge the two corpora and delete any duplicate sentences. From the results, it's clear that the step of removing non-Bengali characters and punctuation from the corpus is crucial. This is also the trick that contributes most to enhancing the model's performance. Finally, 6-gram language model is obtained using the commands from step 3 and step 4. And the training code and the inference code has been open sourced. Those interested can find the corresponding code in the link provided. So, since I didn't use the internal speech recognition data, for me, employing a large model and a strong data augmentation was very helpful in improving the final performance. And it is crucial to delete all non-Bengali characters in the crop, and including the punctuation. I have tried leaving these characters intact, but the improvement achieved was negligible. For me, the experimental attempt with Hubert and Whisper was surprising, as I had the impression that these models should perform better than Web2Vector 2. Yet the results was the contrary. And furthermore, I also tried the denoising model, FilterNet, and however, the outcome was unsatisfactory too. If I had more time, I would attempt to train a spiral correction model and experiment with model assembling and predict punctuation. But I didn't try this. I also tried Umang's MMS1B model, and whose license is CCNC. Its performance is impressive, and I believe replacing Web2Vector XLR SR1B with it would yield even better results. I believe if the dataset provides the start and end times of each character in the speech, it would be better. Maybe possibly enabling me to do some character level data augmentation. And my English proficiency is not very high, so